So is microphone on? Yeah. Okay. So thank you, Chancellor Yang. And one of the things that's the most wonderful about this award is it's a chance to speak, which is very rare, a chance to speak to the whole campus community and also to people from outside the campus. So thank you all for coming to hear me speak. So my introducers have already given away a lot of my laugh lines, but my talk is about a battle between two of our great theories of physics, the theory of the very large and the theory of the very small. And it might look like a rather uneven battle, but the fact is it has gone back and forth, and often the little guy has gotten the better of things. And actually, right now, it's in a very interesting phase, largely due to work done here at UCSB. So I'll start with a couple of quotes. The first from Albert Einstein: "God does not play dice with the world." So what he was talking about is this. The classical picture of an atom is a little solar system, an electron going around a nucleus in a predictable way. The truth, what quantum mechanics tells us, is very different. It tells us that if we go looking for that electron, we cannot know in advance where we're going to find it. We can't predict it even in principle. There's a basic randomness in nature. There's a probability cloud which says where you're likely to find it, but each time you look, you'll find it in a different place and no way to predict where. This is what Einstein was objecting to. But now we know this theory accounts with great accuracy for properties of atoms, matter. Our entire electronics industry, which is some large fraction of our economy, is based on our ability to control quantum mechanics. So that's the first quote. The second quote, though, from Stephen Hawking says that things are even worse than Einstein feared, because God, he says, not only plays dice, he sometimes throws the dice where they cannot be seen. This quote comes from the paper which pointed out this conflict, which is still unresolved today and which I'll be talking about. So the big picture is that around 100 years ago, we had three great revolutions in physics: special relativity, general relativity, and quantum mechanics. And these revolutions changed the way we think about space and time and matter and even reality itself, the bit with the dice. And now 100 years later, these still form the basis for our understanding of these things: space and time, matter and reality. But our work is not done, because these new principles were discovered one at a time. And when you try to fit them together to understand what the whole picture is, you run into challenges. And meeting those challenges and finding how to fit these together has really guided a lot of the physics of the last century and is still going on today. So let me start with each of these new theories says that things behave in unfamiliar ways if you go to extremes. Special relativity if they're moving very fast, general relativity if they're very massive, and quantum mechanics if they're very small. So a natural question is, what, for example, if something is both very fast and very small? And shortly after, and so we have both, special relativity and quantum mechanics in play. So Paul Dirac asked this question shortly after the discovery of quantum mechanics. Now, this is a public lecture. I know there are a fair number of physicists here, but I also know there's a lot of people from all sorts of backgrounds, and you're not supposed to have equations in a public lecture. So think about this as a piece of art. But this piece of art is very powerful because it allows us to understand to great accuracy the properties of matter, the properties of properties of atoms, of molecules, of matter. It's a fantastic description, a single short equation that encodes so much of nature. But it can't be the whole story, because this equation fails for particles that are moving very fast, close to the speed of light. This equation incorporates the quantum principle, but not special relativity. And so Dirac set himself the problem of finding an equation which would be better, which would work even for very fast particles, and he succeeded. Another piece of art here, the Schrodinger equation, the Dirac equation. So what Dirac had done is he found an equation which, for slow-moving particles, agrees with the successful theory we already had, but it correctly incorporates special relativity. It correctly describes the behavior of things moving close to the speed of light. So he succeeded, but in addition to succeeding at what he set out to do, he got an unexpected bonus. At first, it didn't seem like a bonus. Well, the bonus was that this equation has twice as many solutions as he expected to find. There are the ones that he expected that were just the ones that we already had, but working a little bit more accurately, but then a whole new set of solutions that had no obvious interpretation. And what he eventually realized was that what his equation had predicted an entire new set of particles, an antiparticle for every known particle with the opposite charge. And antimatter, specifically the positron, was discovered by Carl Anderson just a couple of years later in high-energy particles from cosmic rays. So this program of combining these principles is very fruitful. Actually, the story of special relativity and quantum mechanics didn't end with Dirac. It's gone on. It's actually driven much of the physics of the last 100 years. It required the development of a new mathematical language, quantum field theory, and also it's played a big role in recent understanding. So I'm sure you've all heard of the discovery of the Higgs boson a couple of years ago, and our own UCSB experimental group played a very large role in this. The Higgs was really, well, the end of a series of experimental discoveries. So 40 years ago, more than 40 years ago, we theorists put together the Standard Model, which seemed to be a theory of all known particles, but it also predicted 5 more that had not yet been seen. And one by one, they've been found. Again, UCSB played a very big role in the discovery of the top quark. One by one, they've been found with just the predicted properties. And the fact that one could make such precise predictions, the fact that before there was any hint that these particles existed, one could anticipate not just their existence, but their detailed properties, is because of the combined power of special relativity and quantum mechanics. They're very hard to fit together, and so when you succeed in fitting them together, you learn a lot. You obtain a structure which is extremely predictive and teaches you things you didn't expect to learn. So that's special relativity in quantum mechanics. General relativity will be much harder. So again, quantum mechanics becomes important for very small objects. General relativity becomes important for very massive objects. And now for something to be both very massive and very small means that you're in some kind of extreme environment. But there are several. One would be particle collisions at extremely high energies. One would be the early moments of the Big Bang. The universe is expanding. We can follow its expansion backwards. In the past, it was smaller. It was very, very much smaller. And we can reliably, observationally follow it back to a time when it was vastly smaller and denser than it is today, and when quantum mechanics and general relativity were both acting together. And the third, the one which will be the focus of much of my talk, will be, singularities, near the centers of near black holes. Now, I'm talking about the interesting thing. The thing I'm talking about is the conflict, the places where these two theories don't get along, and we have something new to learn. But it's worth reminding you that in fact there are places where the two theories work quite well together, and it's quite a beautiful story. So there's the question. This is a picture, a very deep field picture looking far out into the visible universe of galaxies of various distances. And the question is, why are there galaxies at all instead of just a uniform gas filling the universe? And once you answer that, what determines the pattern that you see, the sizes of typical galaxies, their separations, their distribution? And it turns out that the answer, remarkably, is quantum mechanics. We now understand and have very good evidence that the theory is right, that what you see here, again, we're a tiny, tiny bit on one of those, on a spot like one of those, that what you see here, this cosmic pattern, began with these tiny randomnesses of quantum mechanics I talked about. I talked about how, because of randomness, there'll be, early in the universe, when it was very, very compact, because of quantum mechanics, there'll be a little bit more matter in one place than another. It won't be perfectly uniform. And as the universe expands, these non-uniformities grow and then begin to sort of collapse, and the result is what you see. And this explains not just the galaxies, but it explains one of the other great observational signatures of the universe, the cosmic microwave background. Here's a plot of the hot and cold spots on the early universe, produced again by a collaboration that includes Phil Lubin on our faculty. And here's a plot of the distribution of sort of the noise and the theory, and as you see, the data fit again extraordinarily well. So this is really beautiful. The theory is very small and the theory is very large are working together, and remarkably, we can test it. We can see that it works. This pattern, the pattern up there, the radiation was emitted when the universe was a few 100,000 years old, a small fraction of its current age. But the pattern actually formed when the universe was less than a second old, or at least, really, really early. So here's a success of quantum mechanics and gravity working together. But we want to go further. We want to push back. We'd like to have, among other things, a theory of the Big Bang itself, the initial, the beginning of time, whatever it was that kicked this off. And when we push back too far, at some point, our existing theories break down. So this is a question we want to be able to answer. So the early universe is one place where these two theories potentially butt heads. Another is black holes. Now, as Kumkum has already mentioned, many of you have seen Interstellar, and so you know that this is not really what a black hole looks like. But Christopher Nolan had a much bigger budget than I did. Actually, how many of you have seen the movie? Well, good. I'm sure there are some of you who have not yet seen it, and I hate spoilers. So I won't say much, but I don't think it's a spoiler to say that in the movie, the scientists get to observe a black hole up close. We don't have that luxury, and so we, instead of doing sort of real observations on black holes, we are going to have to do thought experiments. And so before I move ahead with the actual physics, I want to talk about thought experiments and how they can work, and I want to do that by talking about my favorite example, which is Maxwell's equations, the laws of electromagnetism. Again, these are more equations, but it's okay because they're on a t-shirt. So these laws govern the behavior of electric and magnetic fields. But actually, when Maxwell was a boy, this is not what his t-shirt looked like. It looked like that. There was a missing term. I got a few chuckles. People don't usually laugh there, but it is a joke. They didn't actually write equations on t-shirts in the 1800s. But anyway, when Maxwell got into the field, these were the equations, and they were, they had been discovered experimentally, and I want to say a little bit about them. So this bit here is Gauss's law. It says that electric charges produce electric fields. This bit is Ampere's law. It says that electric currents produce magnetic fields. Faraday's law says that oscillating magnetic fields can also produce electric fields. And these were discovered and confirmed by a tremendous amount of data. They were consistent with all known measurements, observations of electromagnetism in Maxwell's day. But they had a problem, and the problem was exposed by a thought experiment. The thought experiment is simply to consider a rapidly oscillating current with a break in the circuit, a capacitor. And the problem is that if you use those equations to calculate the magnetic field next to the capacitor, you don't get a definite answer. You get two different answers depending on how you use the equations. So there's something wrong. Even without doing this experiment, you know that there is something wrong with those equations. And from this clue and a lot more reasoning, some of which I'll mention towards the end, Maxwell was able to figure out that he could fix this by adding one more term. So there is without the term, and there it is. This is Maxwell's term. And with this, the equations give, they're mathematically and physically well posed. They give unambiguous answers to questions like the one I mentioned. Now, Maxwell got a huge bonus because, okay, Faraday's law says that an oscillating magnetic field produces an electric field. Maxwell's new term says that an oscillating electric field produces a magnetic field. So each can produce the other. And so you can get a disturbance which is self-sustaining and which doesn't just sustain, but it moves. So Faraday, Maxwell, you get a self-sustaining disturbance which moves at a velocity that you get from the equations, and the velocity is the speed of light. So Maxwell got a huge bonus for understanding the unification of electricity and magnetism. He understood the nature of light. When I first heard about this in high school, I thought it was the coolest thing, and I still do. You know, it's what we're all trying to do. But you've now seen actually. So anyway, so here's the T-shirt after Maxwell with the last line. Oops, sorry. No, that there's this Maxwell's term is missing. So and then there was. Okay, you get the idea. You've seen now in two examples that this program of finishing the laws of physics, of uniting the principles we already have, often leads to unexpected discoveries. In the case of Dirac, it led to the unexpected prediction and discovery of antimatter. And in the case of Maxwell, it led to the understanding of light. So, you know, if you ask why we're trying to do what we're trying to do, which is very hard and in some ways very remote from experiment, this unification of gravity and quantum mechanics, I can list three reasons. The first is it's unfinished business. We have these three great theories. They're wonderful. They're beautiful. They work very well. And the fact that they don't play well together is a problem we have to solve. The second is, again, as I mentioned, this is the key to understanding the beginning of the Big Bang. And third, the experience that when you figure out how things fit together, you learn things that you didn't expect. So, good. So what do I mean by a thought experiment? Consider various situations, and from now on, all the situations will involve black holes. See what quantum mechanics predicts, see what general relativity predicts, and if they disagree, we get an important clue. So again, here is my black hole, and general relativity, the basic principle is that gravity emerges from the bending of space and time. That's why this extreme bending here is supposed to be exhibiting some very deep gravitational well. If you're standing near the edge there, you're going to be sucked in by the curvature. And this is the fate of very massive objects. Past a certain point, their internal pressure can no longer support them, and inevitably they will collapse in an uncontrolled way. And Einstein's theory says they collapse down to a perfect mathematical point. Nothing can stop them before. It's clearly an extreme bending of space-time. There's infinite density mathematically at the singularity. So the singularity is clearly a very dramatic place and probably something that we need to understand better probably Einstein's theory isn't the final word on it. But there's another place that turns out to be extremely interesting as well, and that's the event horizon here. So the event horizon is the point of no return. It's not as dramatic as the singularity, seemingly. It's just, according to Einstein's equations, a smooth bit of space. It simply is where the well has gotten so steep that once you're past this, you can't get out, and nothing can get out. If you try to shine a light beam out, it will move upwards, and before it reaches the horizon, it will bend back down, and you and your light beam will all end up in the singularity. So the singularity and the horizon are the two things to remember about black holes. Horizon is the point of no return, but otherwise it doesn't seem to be a special place. There's no dashed line there as you pass it, or there's not supposed to be. So starting about 40 years ago, people started to pose this kind of thought experiment, and they exposed two different conflicts between what general relativity said and what quantum mechanics says about black holes. One is the entropy puzzle, and one is the information paradox, and the latest sort of incarnation of the information paradox is the black hole firewall. So the entropy puzzle. In general relativity, every black hole looks essentially the same. Black holes have no hair. Quantum mechanics, on the other hand, points to an atomic, some kind of atomic structure to the black hole. And there's a couple evidences from this, which I'll talk about briefly. So one of these thought experiments that was begun by Jacob Bekenstein in the 70s was to ask the question how much information, how much data a black hole could store. Because, and there's a calculation which I won't go through, but I'll tell you what the idea is. There's a certain minimum amount of energy that it takes to add one bit of data to the black hole. In order to fit it inside, quantum mechanics puts a limit on how much energy you need. And the black hole has some total energy, which just comes from Einstein's equations. And so by dividing the total energy by the energy per bit, you figure out the number of bits that the black hole might hold. That was the first indication that something atomic was happening. The second came a couple years later when Hawking discovered that black holes aren't really black. They glow very faintly. They radiate as though they're a hot body. When you heat something up, it radiates heat. If you heat it up a lot, it radiates light. And that's the kind of radiation black holes produce. And that means that black holes have a temperature. And you know that temperature ultimately comes from the motion of atoms. And so this strongly suggests that black holes, too, have some kind of atomic structure. Not the same kind of atoms that make up matter, but some kind of atomic structure. And he could calculate from his reasoning the number of atoms and came to the same expression. And so the question is, what are these bits? Now, this slide, so I'm actually going to go through a fragment of an equation there because there's something interesting not just about the fact that the bits can be counted, but the number is interesting. So when you look at this expression, three of the things that you see, the speed of light, c, the gravitational constant, g, and h bar, which is the constant of quantum mechanics, are just constants of nature. And there's one thing which depends on the black hole. That's the black hole radius. And the interesting thing is that the number of bits depends on the square of the radius. Now, if you have a box, cubic or spherical, it doesn't matter, the number of atoms or grains of sand you could put inside it goes as the cube of its radius, or the cube of its length. It's the length times the depth times the height, width, depth, height. And so for normal matter, the number of atoms in a block of matter goes as the size cubed. For black holes, the number is very large, but it only goes as the square of the size of the black hole. The square is not a measure of the volume of the black hole, but its surface area. And in fact, this principle, when you look at different sorts of black holes, it very clearly is the surface area of the event horizon, that imaginary surface that governs the number of bits of information the black hole can hold. And this is strange. It's as though these fundamental atoms of black holes and ultimately the fundamental atoms of space-time, instead of filling up space the way ordinary atoms do, they live on the surface of the system. And this has been dubbed the holographic principle. And it's believed there's some evidence that it's a property not just of black holes, but of all systems in quantum gravity. That in gravity, the basic building blocks, the basic things that everything else is made of, they aren't really tiny and sitting at, at little points the way atoms do. They are somehow smeared out in a way that is really unfamiliar in any other area of physics. And the local physics that we see emerges from their dynamics. This is called the holographic principle, and it's a radical change in the nature of space. The other thing, the thing I have to add about black holes now is, so that was the entropy puzzle, the fact that black holes seem to have an atomic structure. The second bit is that they seem to destroy information. And to explain how they destroy information, I first have to explain how they evaporate. So one of the things that quantum mechanics says is that if you look at empty space, really on a microscopic scale, it's not so empty. All the time, little pairs of a particle and its antiparticle are popping into existence and then popping out again. And that seems strange, but if you do extremely precise properties, for example, extremely precise measurements of the energy levels of atoms, you can see that this effect is going on, and it's affecting the way atoms themselves behave. So this is a real thing. But now, if this happens near the black hole, every once in a while, the pair will pop into existence near the horizon. One of the pair will fall behind the horizon and be lost, and the other will escape from the black hole, carrying away, as everything must, some energy. And so the black hole, instead of being something that just always sucks matter in, always gets bigger, due to quantum mechanics, it can also lose energy, and it does it at a steady rate. Now, this is another calculation that uses general relativity, the curvature of space, and quantum mechanics at the same time. But again, it's one that we trust. It's like the calculation, again, of the pattern of galaxies. It uses these two laws in a regime where neither of them is being pushed to an extreme. But once we have this, Hawking argues, we take it one step further and we run into a problem. So here's the process I just described, and after it happens many, many times, the black hole is gone. All of the mass will eventually be carried away by these particles that are being emitted, and eventually the black hole will be gone, and all you have is the outgoing Hawking radiation. Now, another thought experiment. Suppose that early in the life of the black hole, we throw a book behind the event horizon. Once it's behind the event horizon, it can't affect anything that happens later. It can't affect the pattern, the state of the outgoing Hawking radiation. It doesn't matter whether we throw in Hawking's book or my book or a brick. As long as they have the same mass, they will have the black hole will, once that disappears behind the horizon, the final state will be the same. And now this is a strange thing from the point of view of the laws of physics, because the laws of physics, they have a certain kind of property. So the way they work is, if we tell you how the system starts out, then the laws of physics, Newton's equation, whatever equation you're using, it tells you what it looks like as time goes on, and it tells you then what it looks like much later. But the laws of physics are all kind of mathematics that's reversible. They also have the property that if you know how the system ends up, you can run them backwards and figure out how it began. And in particular, the laws of quantum mechanics have this property. You can run them in either direction. But Hawking is now saying that you cannot do this, that the final state doesn't depend on what went into the black hole. You can never, from this final state, recover the past history of the black hole, and so information is lost. And this means that we have to modify the basic form of the laws of quantum mechanics when we apply them to black holes, and probably then when we apply them to anything else that has strong gravity in it. And so this is a direct conflict between quantum mechanics and general relativity. And this is the origin of the quote that I began my talk with. So we have there's more choices, but the two principal choices are that information is lost, meaning that we have to modify the laws of quantum mechanics, and in what seems like a pretty ugly way. Or if information escapes, it means that we violate relativity because somehow information has to travel faster than light. Light can't get out of a black hole. If information is escaping from inside a black hole, it has to travel faster than light. And so we have to modify or give up one of our great principles of physics. That's what he was saying, and it upset a lot of people. And people tried very hard to find his mistake. They're still trying. We now think we know the answer, but in a very indirect way. It involves something called duality. So one of the funny things about quantum mechanics is that light can behave either like a particle, like a wave, or like a particle. It just depends on how you look at it. And that's true of everything. Electrons can behave either as waves or as particles. And so duality is something that can happen in a quantum system that a given thing can look very different depending on how you look at it. And in recent years, we've actually discovered that this phenomenon is very general. We've had a lot of examples that go far beyond waves and particles. And Juan Maldacena found a duality in which something could look like a black hole, the thing we're trying to understand, from one point of view, and a much more ordinary system, just a gas of strongly interacting particles, something that we understand very well, something we even produce in the laboratory from another point of view. And this is astonishing. Like Maxwell, this is and Dirac, this is a completely unexpected connection between widely different areas of physics. There was no clue that this and this had anything to do with each other. And also, this is something we in principle understand very well. It's a theory we understand very well. This has all these puzzles. But now we can use our understanding over here to answer questions over here. This is our most complete theory of quantum gravity yet. Now, Henry, in his introduction, mentioned string theory a number of times. I contributed to string theory. I'm regarded as a string theorist, and yet I haven't mentioned strings yet. They actually play an important role here, because if you look closely, they actually provide the equals sign. They actually, although there are no obvious strings either here or here, the connection between these two very different areas of physics actually goes through string theory. And I should have probably also tried to put a D-brain in there because they play a key role as well. So strings, again, are this idea. So coming from a totally different direction, from trying to solve problems with high energy scattering in gravity, people hit on the idea that it would be an improvement if fundamental things, instead of being little points, were little loops. And by taking this idea and by asking what does it say about the black hole information problem, Maldacena and others were led to recognize this duality. And it has many consequences. First of all, again, since the ordinary nuclear particles satisfy the usual laws of quantum mechanics, black holes must as well. Information can't be lost. This provides the bits that were anticipated by Bekenstein and Hawking. There they are. And the bits are holographic, meaning that you can't tell from the picture, but these things are kind of quantum jittering all over the place, and they really kind of live on the surface around the black hole. So it actually satisfyingly confirms many things that had been guessed at from the kind of reasoning I talked about. So we're not done. If we were done, I'd be talking about something else. And the reason, well, what problems remain? The first problem is, where was Hawking's mistake? exactly how does the information get out? We have this argument based on this duality that it can't be lost. And in fact, a few years after Maldacena, Hawking publicly conceded and paid off a bet that he had been made. He conceded information is not lost. But his original paradox is still there. The argument that information is not lost is rather indirect. We don't understand how exactly the information gets out. And also these new things that we've learned, this duality, which allows us to understand quantum gravity better, and this holographic principle that goes along with it. We understand them kind of in some environments like near a black hole, but how do they work in the Big Bang? How do they work in our expanding universe? That's what we really want to know. And so we have this question, and we have this question, and we're still pushing on these. And the thing which has made this subject so lively in the past few years is that from pushing on these, we found a new paradox, a new place where things don't fit in the way that we thought they did. And this has led us to a lot of new ideas. Let me start with the things that we believe were true, which we're going to have to probably give up something. One of them, again, is that information is not lost in black holes. And the following were also believed. It was believed that although something funny is going on, an observer who stays outside the black hole doesn't see anything unusual. And also an observer who jumps into the black hole does not see anything unusual. What's going on is sort of a new what was believed to be going on is sort of a new relativity principle. It's not that information is traveling faster than light to get out of the black hole. It's that different observers see the same information in different places. An observer who falls through the horizon sees it on the inside. An observer who sits on the outside sees it coming out. And that seems very strange, but they can't compare notes. So it seems like kind of a satisfying resolution. But in trying to make this work, we found after failing to make a model of this many times, we found that there was a basic inconsistency. So here are my partners in crime, my brilliant young colleague Don Maralf, and two graduate students, Ahmed Al-Amheri and James Sully. And so I'll tell you, our argument is really very simple. But it rests on another strange thing about quantum mechanics called entanglement, which is even stranger than the randomness. So since I started with dice, I'll use dice to try to explain. Entanglement is the weirdest thing about quantum mechanics. It's a thing which has no analog in our normal experience. Suppose we have a pair of dice, and they're trick dice in the following very strange way. We roll the first die, it comes up, whatever it comes up, a 1 or a 4. Then we roll the second die, and whatever the first die came up, the second one automatically comes up so that the sum of the two is 7. You always get 7. Or it could be any number. Oh, and you always get 7. So how do you do that? How can the second die know what the first die showed? And this would work even if the die were separated by many light years. And this what I'm describing here actually is a basic property in quantum mechanics. It can happen. It's called entanglement, and it's well. So what we showed is that by thinking about entanglement, that these various things that everybody believed, you couldn't make it work because they imply an impossible state, an impossible quantum state for the radiation. So one of the things about this Hawking process is that the particle that flies away and the particle that falls in are entangled in the way that I described, meaning that they're either both there or neither is there, so they're entangled. But also, information being conserved, what that really means is that each outgoing Hawking particle has to be entangled with some combination of the other Hawking particles. So if I'm this outgoing Hawking particle, I have to be entangled with my infalling partner, but I also have to be entangled with something that's with the earlier Hawking particles as well. And that is not, quantum mechanics does not allow this. There's something called monogamy of entanglement. This Hawking photon has to choose either this or this. You can't have both. You're either entangled with your partner or you're entangled with one of your earlier buddies. And so you have to choose. If information is lost, if this happens, information is lost. If this happens, something bad happens because you lose the entanglement that you were supposed to have between these two degrees of freedom. And when you lose that entanglement, it's sort of like breaking a chemical bond. It costs energy. And the breaking of these bonds in the quantum fields across the horizon produces a wall of energy. That's what we call the firewall, which is not the best name, but it's stuck. And so the conclusion, if you assume information not lost, we really believe that, and you follow it to its logical conclusion, you find that instead of the smooth space that Einstein's theory predicts, something very dramatic happens, probably so dramatic that space just ends, that the interior of the black hole is gone entirely. And so again, we have this conflict between our understanding of quantum mechanics and our understanding of space-time. So this was my main theme, so I should actually keep score a little bit, because when Hawking wrote his paper, when he said that information is lost, he was saying that quantum mechanics loses, that our theory of space-time is good, quantum mechanics loses. When Maldacena came along, he said, no, quantum mechanics is just fine, but space-time is modified in this way, which is in some ways radical and in some ways subtle. It becomes holographic, but subtle. And now what we have said is that if you really take quantum mechanics and follow it to a conclusion, space-time is modified not just in some kind of subtle way, but in a very dramatic way. Now, very few people believe this. As with Hawking's original paper, people are working hard to find our mistake. And as with Hawking's original paper, they may find our mistake, but if there's a mistake, then we'll probably require something really interesting and new in its place. The problem is that there's no mechanism. What we've given is an argument by contradiction. We've shown that there is no quantum state that has all the properties one wants. The information is conserved and that space is smooth at the horizon. So it's an argument by contradiction, but it doesn't explain the dynamics that could form such a dramatic thing in a place where space could be smooth. And so it's actually a pretty simple argument. When we found it, we were surprised no one had ever said this before, but as we talked to people about it, we made them just as confused as we were. And most of the attempts to avoid this conclusion are going back. So now it's been a little over 2 years and about 250 papers, and there is very clearly no theory of what's going on and very little consensus. Most attempts to evade this conclusion go back to relaxing, to loosening the rules of quantum mechanics. So in order to save space-time, people are going back to modifying the other theory. Now, this is hard to do. One of the things that I'm sure you've heard, and it probably comes through from my talk with the randomness and the dice, the entanglement, is that quantum mechanics is weird, but it's a controlled weirdness. It's a predictive theory. It's actually a good scientific theory. The thing about quantum mechanics is if you start trying to modify it, the weirdness often becomes a real thing. The theory ceases to make sense. And so it's very hard to find a theory which looks sort of like quantum mechanics without really being quantum mechanics. Nevertheless, I won't go through them. There's a long list of things that people have tried. Again, there's no consensus. I highlighted the word entanglement. Again, that's the mysterious property that I try to describe with the pair of dice, because It's a very fundamental property of quantum mechanics. It is something which really, in many fields of physics actually, has come to the fore in the last few years. In condensed matter physics as a kind of property, a diagnostic of exotic phases. In quantum information theory, it is central to sort of writing the software for quantum computers. And now in string theory, in quantum gravity, it is playing a central role in, first of all, in creating a problem for the understanding of quantum mechanics and space-time, but it may also provide an opportunity. It may be the key to where space-time comes from in the first place. But really, these are all scenarios. They're frameworks. They're not theories. They're people, we have a problem, we have to give up something we believed, and we're at the stage of saying, well, let's give up this and see what happens. Let's give up that and see what happens. I should mention again that actually UCSB, ever since I've been here, more than 20 years and before, has really been a center for quantum gravity. It's played a unique role in the field, and many of my colleagues have contributed to the subject. Gary Horowitz is the author of one of these modifications of quantum mechanics, and I put a star there for Steve Giddings because he's one of the few who's taking another direction, exploring the possibility that actually there is some mechanism that physically transports information faster than the speed of light. But there are many things being tried, and it's extremely interesting that there's no knowing which of them will be true. So there are questions that naturally are asked, and I can't answer them, so I'll ask them right now. Are there any observational effects for black holes? Are there any consequences for the early universe? And it's far too soon to say because we don't know, again, what the answer is. We don't know how this is going to come out and what we have to give up and what is going to be part of a more complete theory. Just to recap what I said, this program of trying to understand how quantum mechanics and gravity fit together has led to a number of remarkable understandings. That black holes have an atomic structure, that space is in some sense holographic, this remarkable duality of Maldacena. Now, I started with I didn't start with Maxwell. I talked about Maxwell and his thought experiment, but he wasn't actually able to leap directly from the thought experiment to the answer. He went through a lot of stuff. He built models of electromagnetic fields in terms of space being filled with little vortices and with little wheels and gears. And I know that when I was a student, I thought this was very funny. I mean, that doesn't, looks hard to believe, but it led him to the right answer. He had a very modern point of view. He wasn't really interested in the wheels and gears. He was interested in the equations that he could derive from them. And once he found the equations, he threw the picture away. And so he was doing exactly the right thing. But I feel that in this subject, we're kind of at this stage now. We're trying on a lot of different crude pictures to see how this theory will eventually look. And so far, we haven't figured out which one is right and how it's going to look. But it's an extremely interesting time to be working on this subject. So, thank you. I'd be totally happy to. Yes. Oh, I'm not sure. We'll start. Yes, please.
So, my understanding of all this is very primitive, but as I was taught it, from the point of view of an external observer,
yes,
it actually takes an infinite amount of time for the particles to enter the black hole.
Yes.
And so I was wondering what's the time to separate.
Yeah.
So that means
good.
That loss of information is deferred indefinitely into the future.
Can you repeat the question?
Okay. So the question, there's an interesting fact which is that if you're looking at a black hole from the outside and someone jumps in or something is thrown in, from the point of view of what you see, it takes an infinite amount of time for the inflowing body never reaches the horizon. And the reason it can't is because we can't see it go behind because light can't get out. So what we're seeing is as it gets closer and closer, the light that it's emitting is taking longer and longer to climb out of the gravitational well to reach us. But that's kind of an optical effect. If you're sitting on the inflowing body, you fall in quite quickly. And also, it's interesting, what this effect would potentially be useful for getting information out, but the problem is as it approaches the horizon, it's also becoming darker and darker because this light that's emitting is being stretched out over a longer period of time. And so there doesn't seem to be any useful way to go from that fact to getting information out. Thank you. Yeah. Robert. Oh, just one? Oh.
What does Hawking think of the firewall?
Okay, very good question. So Hawking does not believe it. The question is, what does Hawking think of the firewall? He doesn't believe it, but so when he changed his mind in 2004, he also, the basic reason that he changed his mind was because, again, of this duality of Maldacinas. But he also wrote a very short paper in which he tried to explain what was wrong with his earlier argument. And no one has understood that paper. It's kind of, and so after the firewall argument, he said he didn't believe it. He more or less reiterated his earlier argument. So, yeah. So I'm happy to answer questions all night, but maybe privately if you want to cut this off.
Well, thank you very much, Joe. Thank you.
Thank you.
Now I know why Mark Trzednicki said that you write very clearly. You also speak very clearly. Thank you.
Thank you.
As part of the research lectureship, the faculty research lectureship, we have a medal that we give you, as well as an honorarium. However, the honorarium has been deposited into your bank account already,
oh, wow.
I hope. So this is a dummy...
so I didn't need to give the talk. I could
It's one of the best kept secrets. I did want to remind people that the call for nominations is open for the next faculty research lecturer. We need to keep Joe busy, so please put in those nominations as you go ahead. And now Chancellor Yang will present the medal to Joe.
Joe,
Thank you. Thank you.
It has your name on the back.
Thank you. Thank you. Thank you. I'm happy to take questions all night. I'm going to keep it on the stage.
Congratulations again, Joe. Joe is happy to talk to people about his work. He says he's happy to take questions all night. But on behalf of Chancellor Yang and the Senate, I'd like to thank you all for coming and to thank Joe for a very fascinating lecture. Thank you again, Joe, and congratulations.